Hello, everybody. Thank you for joining us for today's digital water expert session, Predictive Modeling in Texas and Beyond, How Machine Learning Helps with LCRR/LCRI Compliance. My name is Jay Nelson, and I'm the marketing lead here at Trinnex. I'd like to welcome you all. Thank you for joining us today, and I'll start by covering just a few key housekeeping items. Today's session will be about 45 minutes of presentation with time for Q&A at the end. The session today is being recorded, and everybody who signed up will indeed get a copy of the recording sent to you directly following today's session. We encourage everybody in the audience today to submit your questions and poll responses to our panelists. We at Trinnex love to understand where you, the audience, are in your digital water journey. And this is a big reason why we host these sessions. We aim to build community through providing practical viewpoints, innovation tips, and also give you the chance to have your questions answered by the experts who join us on these sessions. I'd like to request all attendees, please submit your questions using the Q&A panel at the bottom of your screen. This will ask your questions directly to our speakers, Wendy and Katie, today. It helps us stay organized so we can see and track all of your questions coming in. We may not get to all of these questions live, but please go ahead and ask away. We'll do our best to respond to each question personally, whether live during the event today or in a personal follow-up if you do not get your question answered. Okay, let's get started. For today's agenda, we'll be covering first introductions to Trinnex and our speakers for today. There, we'll jump into predictive modeling and why it is a helpful tool. We'll talk a little bit about the varying regulatory perspectives out there in regards to predictive modeling. And then we'll go into a more in-depth overview of how predictive modeling works, our journey, and how we approach it here at Trinnex, as well as some success stories that we've seen out there. And finally, we'll have time at Q&A. So one last reminder, please do add your questions in the Q&A panel so we can have a good discussion at the end of today's presentation. So I'd like to start by first introducing Trinnex. Perhaps you've joined us on one of our webinars before, but in case you have not, I'll just share a little bit about us. Trinnex helps infrastructure leaders advance their digital journey through proven processes, software tools, and consulting partnership. Our team has decades of water industry domain knowledge, data science expertise, and an unmatched commitment to technical software excellence. We deliver innovation that is backed by this experience. Our team consists of digital water industry leaders with a proven history of bringing products to the market that our clients love. We've been in the industry long enough to be experts in the field. We're agile enough to pay direct attention to your unique needs. And we're ambitious enough to deliver the next generation of technology to help you in your day-to-day. Ultimately, this uniquely positions us to deliver software designed by water experts for water experts, like everyone who's joining us in the audience today. And with that, I'd love to introduce today's speakers, Wendy Lundeen and Katie DeHeer. Wendy, thank you for joining us today. Wendy Lundeen has more than 24 years of experience in water, wastewater, civil, planning, design, and construction. She has worked on a range of projects including water treatment plants, wastewater treatment plants, water wells, aquifer storage and recovery, lead and copper rule revision/improvement compliance program management, biosolids, master planning, small to large water and wastewater conveyance, stormwater and source water protection, large diameter water lines in Texas, municipal wastewater programs in Louisiana and Texas, infrastructure master planning and technical interface management for oil and gas operations in West Africa and Southeast Asia. Wendy's a senior project manager and principal with CDM Smith in Houston, Texas, where she's been based for the past 9 years. So as you can tell, just an incredible breadth of knowledge and expertise with Wendy joining us today. Thank you so much, Wendy.
Glad to be here.
We are also joined by Katie DeHeer. Katie is a product leader at Trinnex and the architect of LeadCast Predict, the predictive modeling module within LeadCast. Katie holds dual master's degrees in business administration and business analytics, and Katie has over 14 years of experience in analytics-driven research, machine learning, and data visualization. Katie engages with utilities and regulators across the country on how to apply predictive modeling to protect public health and optimize resources. And I will say she does an excellent job of doing that and an excellent job of representing Trinnex. So thank you for joining us today, Katie.
Thanks, Jay. Happy to be here.
Glad to have you. You can find both Katie and Wendy on LinkedIn. If you're on that social media network, feel free to give them a follow for more insights around predictive modeling. So before we jump into the material, I would love to get a pulse check on the audience through a poll. I'll be launching the poll shortly here, but our question will be, what is your level of familiarity with predictive modeling? It'll be a big topic of today's discussion, so we'd love to hear the audience's viewpoint on that. We're seeing some really good answers coming in.
Always curious to know where this one lands, Jay.
Yeah, it's a good question, and I think will be very pertinent today's discussion. Getting a lot of good responses. Give it just a little bit longer. Right. Thank you, everybody, for submitting your answers. We'll close out the poll in just a few seconds here and share the results. So it looks like most people, first of all, thank you everybody in the audience for submitting your responses. Most people have either said they are new to this and seeking help, or they've dabbled before but are interested in learning more. We've got a few experts in the audience, so it's great to have all of you here. And I think no matter where you are in that journey or your level of familiarity, you're going to definitely find some value information as a part of today's discussion. So thank you everybody for taking part of that. With that, Wendy, I will pass it over to you.
All right. Thank you, Jay. Appreciate it. So as we look ahead to the 2027 deadline for the lead and copper rule improvements baseline inventory submission, one of our key challenges is managing unknowns in our service line data. Unknowns, by their very nature, represent uncertainty. Their prevalence increases our annual replacement targets and ultimately drives up costs to utilities and ratepayers. This is where predictive modeling and other tools like machine learning and statistical analysis can become one of the most effective tools in our toolbox for protecting customer health in a cost-effective manner. So the objective of predictive modeling is simple but powerful: to reduce the number of unknowns in our inventory in a cost-effective way. By using existing data, such as parcel records, construction dates, permit history, and past replacement results, combined with a relatively small sampling of random field verifications, predictive models can estimate the likelihood of a lead service line at a specific location or home. Now, this doesn't completely replace the need for field verifications, but it does allow us to focus our resources more strategically. Every unknown we can confidently resolve through modeling reduces our annual replacement obligations. So fewer unknowns means fewer assumed lead lines, and that directly translates into lower targets and less unnecessary excavation, which allows us to focus our limited resources on areas where we can improve customer health. I'd also like to point out that predictive modeling isn't just about meeting regulatory deadlines. It's also a valuable planning tool. So, by identifying areas with higher probability of lead or galvanized lines requiring replacement, we can prioritize where to dig test pits, where to send crews for verification, and where to plan for service line replacements. This allows for smarter deployment of field teams, fewer surprises, and ultimately a more efficient use of budget and time. So as we prepare for the 2027 baseline inventory submission under the LCRI, it's important that we understand how the federal government and state regulators, such as TCEQ, which is the Texas Commission on Environmental Quality, will determine our annual service line replacement targets once that baseline is in place. The calculation is straightforward, but the impact can be significant. Here's how it works. So we take the number of lead service lines, add the known galvanized lines that require replacement, and then add all the unknowns. That total number is then divided by 10, which represents the number of years we have to complete the replacements with a minimum target of 10% per year. So I just kind of want to walk through two examples to show how this can play out with significant unknowns and no unknowns in the system or in the inventory. So here we have two inventories, each with 150 service lines. In the one on the left, you can see there are 2,000 lead lines, 3,000 galvanized requiring replacement, 20,000 non-lead, and 125,000 unknowns. When we do the math, adding up lead, GRR, and unknowns, you get a total of 130,000 lines assumed to require replacement under the rule, with an annual target of 13,000 replacements per year. So depending on how you look at it, fortunately or unfortunately, the system only has 5,000 known service lines that actually require replacement. So in theory, they would then be on the hook to identify and replace an additional 8,000 service lines in that first year alone. Now, if we can significantly reduce the number of unknowns, as shown in the example on the right, the results will tell a much different story. You can see we have an increase in the number of lead and GRR from the first example. However, since we are able to reduce the unknowns down to 0 in this instance, our annual replacement target drops to 1,000, or 1/10 of the 10,000 total replacements required. So even though this utility has more known lead and galvanized lines requiring replacement, its annual burden for replacement is drastically lower because it does not have those unknowns. So this really highlights why identifying and resolving unknowns is so critical. Every unknown counts as presumed lead until proven otherwise, and it inflates the number of required replacements. If we can use tools like predictive modeling, data analysis, and strategic fieldwork to convert unknowns into knowns, we not only meet the regulatory requirements, but we also save substantial time and money while arriving at the same conclusion as more expensive alternatives. All right, so speaking of saving money, when it comes to identifying service line material, we have a whole plethora of tools at our disposal. Historic records, which we've all used at this point in developing our inventories, door-to-door inspections, mechanical excavation, CCTV, as well as other emerging technologies. Each of these has value, but they also come with their own cost in terms of time, level of effort, and money. So the graph that you see here on screen was published in the December 2023 journal, AWWA. And I know it's hard to read, but the details aren't really what I want to illustrate here. On the y-axis to the left, you have the average cost per service line evaluated, which is shown in logarithmic scale. And on the bottom x-axis, you have the estimated accuracy in terms of percentage, with the right-hand side indicating a higher level of accuracy. So the first thing that I want to point out is that none of these evaluation methods are 100% accurate. I think this is one of the key anxieties that those tasked with protecting public health, such as compliance officers or state regulators, get hung up on when considering statistical methods. Unless you dig up the entire service line from the building to the main, you will never know the service line material with 100% accuracy. Even then, you won't be able to verify, what that internal wetted surface area is for that service line. What I want to highlight here with this graphic, which is indicated in the lower right-hand corner, is that predictive modeling offers an approach that can be just as accurate as other methods, including physical inspections, excavation, and historical documentation. But here's the key difference. It can cost just a fraction of what those other methods do when applied across the system. So it's not to say that it's free. Field verifications are still required to train and validate the model, but instead of digging up or visually inspecting every single service line in the system, we can use targeted field data to build a model that predicts service line material with a high degree of confidence across the entire system. Okay, so that being said, and predictive modeling has very quickly gained national traction as a reliable and efficient method for identifying service line materials. So as of today, there are 34 states across the country that officially accept predictive modeling as part of their lead and copper rule compliance strategies. And I'm very pleased to say that here in Texas, we reached a major milestone just last month when TCEQ announced that they are formally accepting predictive modeling for inventory development. It's a big step forward, but it does come with some very clear expectations. So here in Texas, the burden will remain on the utility to demonstrate the accuracy of the model. This means that robust validation through field verifications is critical. The inventory validation pool required to be completed by year 7 is just one of the tools that will be used to assess model performance and accuracy. So, while modeling is still on the table, success really depends on doing it right. With the right approach, we can take advantage of this regulatory decision to reduce costs, streamline planning, and meet compliance deadlines with confidence. So at this point, I'm going to go ahead and hand it over to Katie, and she's going to get into the details of predictive modeling. But first, talk about what regulators might be looking for and what systems should consider when developing their models.
Awesome. Thank you so much, Wendy. So yeah, as you mentioned, TCEQ's stance is that water systems are responsible for the efficacy and reliability of the model. So there are many considerations that go into this. And so what we thought would be helpful is to lay some of those out here. In working with dozens of state regulatory agencies on predictive modeling, these are some of the common themes that come up again and again. And you'll see these weaved in throughout the following slides. But for now, I'll pick a few to elaborate on. So first, it's seen as a best practice to build models with field verified information as opposed to unverified historical records. And that information should be statistically representative of the water system, such that the model can generalize to the water system with at least 95% confidence level. Also, models predict probabilities, right? And the probability threshold that is selected to call a service line non-lead should be carefully considered. You'll hear more about this in the following slides. But additionally, models should be run on an iterative basis alongside continuous field investigation. So this isn't a one and done type of solution. And obviously model performance is really important to consider. This can be measured on a test sets of field verified services and is a really important part of that iterative process. And lastly, it is possible for models to be tricked by newer replaced services in the test set. So we have to try our best to try and account for any historical lead or galvanized materials that have since been replaced. So many of the utilities that we work with have imperfect information about, what could have happened in the past, but it's worth considering going forward. If there's a replacement that happens and the utility is aware of, that's really important information to consider. And then before we get too deep, let me set the table with foundational explanation of what predictive modeling is. So predictive modeling focuses on developing data-driven models that find patterns in data and use these patterns to make predictions. Machine learning is a type of predictive modeling for which models learn from a training data set and are validated with a testing data set. So applying this concept to lead and copper programs, the model is trained and tested on field verified services, along with other information such as property attributes and demographic data. And this information is used to make predictions about the material of unknown services. It's an iterative process. We use the model to guide targeted field investigation, and then we feed the findings from these field investigations back into the model iteratively. Before I get a little more into the weeds and throw a bunch of numbers and technical information at you, here's a cute but practical example of how predictive modeling works. So a model could be trained to tell the difference, for example, between cats and dogs using features like those you see on the screen. So size, head, tail, ears, nose, colors, paws. In the same way, predictive models can be trained to differentiate between service line materials using information like property age and value, the neighborhood, the diameter of the service line, the water main age, the demographics of the area. So some of the sources that we use to predict service line material are publicly available, such as demographic data, housing data, parcels, and tax assessor data. And then we combine that with the utilities service line inventory and any physical verifications and replacements that are known in order to build the predictive model. And so if you are interested in predictive modeling, there are two critical success factors to keep in mind as you're proceeding through your lead and copper programs. So first, keeping track of when services are physically verified under any circumstance is really important. Second, recording when lead or galvanized services are replaced, as I mentioned previously, is going to be really critical. So these might seem obvious, but after working with over 60 utilities across the country on predictive modeling for lead and copper programs, I have learned it's best not to assume that anything is obvious. There are really a lot of moving parts to these complex programs and a lot of little things to consider. So I just wanted to call that out. So here's kind of a 10,000-foot view of how predictive modeling works and how we can actually apply it to service line inventories and replacement programs. The model predicts the probability that individual services are lead or galvanized. And you can see in this example, those predictions are mapped on the left. And then when you aggregate them in 10% increments, you can see the profile or distribution of lead probability for unknowns in the water system. So those predictions near 0% or near 100% are going to be more reliable. So those are the outer edges of the histogram on the right-hand side. So those are the ones that we'd want to label as a definitive material based on the model's predictions. Obviously, we want to target the higher probabilities for potential replacement. And then the middle yellow area on the histogram would stay as unknown. And as we continue to update the model with new information from the field, we see the predictions in the middle shift towards the outer edges where they can be more confidently considered a prediction of either non-lead or lead. But I will caveat that by saying this shift is not always perfectly linear. And a really critical question that we need to consider is, how do we evaluate model results? How do we know the model's accurate? Oops, I jumped forward too far. Here's an example of a histogram we look at frequently of the model's results. This is for a larger utility in the Southeast that we're supporting. And it shows a number of unknowns in the inventory by their probability of lead or galvanized in 10% increments. So this utility has field verified about 4% of their utility side unknowns and 2% of their private side unknowns, for a total of almost 6,000 field verifications. So they're getting started, and that's the data we're using to train the model and generate these predictions about unknowns. So when this utility submitted their initial service line inventory in October, all of that blue bar, which is a large chunk of their unknowns, were submitted as non-lead on the basis of the predictive model. So as Wendy pointed out, that 2027 LCRI submission is going to be really critical. And starting off with removing so many unknowns in the October submission has really set this utility up on a good path to continue reducing unknowns going forward. So now I'll jump ahead to how do we evaluate the results? Pardon me for skipping too far. So a critical question we of course have to consider is how do we evaluate the model? How do we know it's accurate? So we really do have to look at the model performance from multiple angles. One is a binary approach where we look at something called a confusion matrix. So the model predicts the probability of lead or galvanized between 0 and 100%. And in the confusion matrix, we're basically drawing a line down the middle or at some thresholds in between 0 and 100%. And we're saying everything less than a certain threshold is predicted to be non-lead, and everything greater than a certain threshold is predicted to be lead or galvanized. And then we're comparing those binary predictions to actual field verified data. But we also need to look at it from a granular perspective to make informed decisions. So on the right-hand side, there's an example of an examination of the model's accuracy in 10% increments. So when it predicted, closer to 0 and closer to 100%, and specifically less than 10% or greater than 90% probability of lead, it's pretty accurate. We need this level of granularity, and honestly, we go even deeper than this. But just to give an idea of the multifaceted approach to evaluating model performance, we need to do this in order to make informed decisions based on the model's predictions. So we often get asked, what if I don't have lead or GRR? Can predictive methods help me? What do I do? In this scenario, we use a statistical method. So we start with a representative set of field verifications. And if we don't find any lead or GRR in that set, we can draw some conclusions from that. So one conclusion is that the proportion of materials that we observed in the sample is generalizable to the rest of the unknowns with a 95% confidence level. Then there's another way to interpret this too. So that is, given that you did not find any lead or GRR in a representative sample of a certain size, you can estimate with 95% confidence the upper limit of lead or GRR that might exist in the rest of the unknowns. So this all depends on the number of unknowns in the system, in other words, the population, and the number of representative field verifications performed. In statistics, we would call that the sample. So the more representative field verifications that you have in the sample set relative to the population, the smaller that the estimated upper limit of potential lead becomes. So you're essentially reducing uncertainty by increasing your sample size. So the minimum sample size here for statistical analysis would be somewhere between 300 and 400 field verifications. And then if you do find lead or GRR, as the screen shows, the approach would be to use machine learning, and which is a type of predictive modeling. And with this approach, we would build the model, we'd predict the probability of lead or GRR at other locations, and then we'd use those predictions to guide targeted field investigations in an iterative fashion. So let me elaborate a little more on that iterative process. It's an important concept, so I want to make sure it is understood. So essentially, we build the initial model, and then we continuously assess and improve it with more and more field data. So looking at it as an iterative process from an iterative perspective instead of a one and done approach is seen as a best practice in the industry and by regulators. And this is for good reason. We can observe and respond to real world conditions in the field and get smarter as we go. So regardless of the predictive method utilities are using, it needs to start with a representative sample. So we often get asked, well, can we build the model with field data that we already have? And you might be thinking, of course we can. Why would anyone even ask that question? It's field verified data. Well, it's because existing field data is unlikely to have been collected in a perfectly randomized way that makes it unbiased and statistically representative of the water system. However, this is where academia meets practicality. Trinnex has a fill the gap tool that we find ourselves using a lot in this exact scenario, where we use a combination of statistics and optimization methods to evaluate the existing data and recommend additional sites to field verify in order to sort of round out the statistical quality of the sample set. So in this example, this is a utility, a smaller utility in the Northeast. They had already collected many field verifications through customer surveys that were verified by engineers. So those are the red dots. And if you were to just eyeball this and not apply statistics to it, you might say, that's pretty good. It's nice and spread out. Let's roll with it. But when we use statistical methods to dig a little bit deeper, we can see some periods of construction in this example that were underrepresented in the sample. So our algorithm recommends some additional verifications to make up that gap, and those are represented by the green dots. So yes, you can use existing field verification data. You'll just want to carefully consider, is it representative, and is there a gap in representation that needs to be filled? So everyone loves a case study. This is one of a few I have in this presentation. This is Middlesex Water Company in New Jersey. They have about 60,000 service connections across 7 towns. And they plan to replace all lead and galvanized services by 2031. So New Jersey got a little bit of a head start on this with their specific state regulations. So we built the original model for this utility using about 30,000 field verifications that had been collected over the course of previous field work. I'm sure people flinched when I said 30,000, and I just want to emphasize this utility is an anomaly with how much field data they have. They have had a program in place for years where over the course of normal operations, people have been able to enter what they've observed in the field. We don't need that much data for predictive modeling. And I'll get more into how much we do need in the subsequent slides. But for this utility, for over a year and a half, we have been iteratively rerunning the model alongside their continued field investigation and incorporating lots of new field data into the model. So at this point, their predictions of less than 10% probability are over 99% accurate, as you would expect with so much data in the model, right? So we feel pretty good about deprioritizing these properties with less than 10% probability of lead or galvanized with a potential non-lead designation. So for sites that the model predicted greater than 90% probability, that is a high probability of lead or galvanized. It's 96% accurate at this point. That's still pretty good. It means that if we look at all the services in our test set with a predicted probability of lead or galvanized over 90%, more than 9 out of 10 were actually found to be lead or galvanized. We also have to look at some really important metrics called recall and precision. I'll break those down. The model's recall is 97%. This means it is correctly predicting more than 9 out of 10 actual lead or galvanized service lines in the test set. The model's precision here is 90%, which means that when the model predicts lead or galvanized, it's right 9 out of 10 times. So using this model, Middlesex has been able to prioritize inspections at locations that make the most sense, and it's going to save them considerable time and money in the long run. So to give you an idea, here are the latest results, or one aspect of the latest results for Middlesex Water Company. This is after 5 model runs alongside continuing field verifications. So it's the iterative process exemplified here, and they're able to confidently deprioritize field verifications at almost 20,000 premises with less than 10% probability of lead or galvanized. And they're focusing on field verifying anything with 10% or greater probability, which is a pretty conservative approach. And at this point, they have field verified 18% of their utility site unknowns. That amounts to about 11,000 service lines, as well as a staggering amount on the private side. So they started at about 30,000 at this point. After 5 model runs in 18 months, they've got over 40,000 private site field verifications, which is about 66% of the private site unknowns. And again, I just want to reiterate, this is a ton of field verifications. Most utilities we work with do not have near this amount, and predictive modeling adds value for them as well. We'll give some examples in a minute. So on the next slide, we can see a snapshot of the inventory that Middlesex Water Company submitted in October of 2024. So it was down to just 388 unknowns with the help of predictive modeling alongside continued field verification efforts. They started with 30,000 unknowns and they're down to 388. But as I mentioned, this utility has a lot of field data. They are unique, and you can definitely leverage predictive modeling with fewer field verifications. So on the next slide, it kind of helps me identify an answer to this critical question that I've been leading up to. How many field verifications will you need for predictive modeling? So this answer is very nuanced. There are 2 critical considerations. One is model performance metrics, like how accurate is the model overall, how many of its lead or GRR predictions are correct, how many of its non-lead predictions are correct, how much of the actual lead or galvanized in a test set is it actually accurately classifying as such. These are all questions that are answered with different performance metrics, such as accuracy, precision, or recall. And the second consideration is a confidence level. So this is essentially, what is the probability that the observed performance of my model on a test set of field verified services is generalizable to the rest of the unknowns? In other words, how confident am I in the reported performance of the model? So here's an example to kind of try to answer this question, or provide some research around it. Here's an example of how the model's accuracy and confidence level changes with more field verifications. So this is from a study that we did in a system where most of the utilities unknowns had already been field verified, which gave us the opportunity to step back in time and observe the model's performance and confidence level as more verifications were available to build the model. So we simulated this process. So you can see with an initial representative set of 372 verifications, we can estimate the proportion of materials in the rest of the unknowns with a 95% confidence level, and we can build an initial model to predict materials at other locations, but the accuracy of those predictions is going to be a little unstable. The green dots are bouncing around all over the place. So this is just a starting point. We want to continue to collect more field data. So then that second line is with about 1,500 verifications. The model has a overall accuracy level of 82% with a 95% confidence level. And this is where it really starts to stabilize. And with about 20% of the unknowns being field verified and used to train and test the model, the accuracy increases to over 90% with a 95% confidence level. And this time, though, a smaller margin of error, because with more field verifications, you reduce your margin of error surrounding this whole exercise. So how does this study translate to larger systems? The first numbers don't really scale up. Regardless of the size of the system, we need 300 to 400 verifications to start the process. And then with 1,500 to 3,000 verifications, we start to see the performance metrics stabilize at a 95% confidence level. And so, of course, if you are a larger system and it makes sense to divide your system up into, sub areas for modeling, then, if you're doing modeling on 2 areas within one system, you would double those numbers. But you get the idea. Per model, those first 2 numbers don't scale up. But getting to the 3rd step is much more variable. And it depends on the clarity of the trends and patterns in the water system and the model's ability to pick up on those. So it's impossible to estimate exactly how much more field data is needed here. There's not an equation or a crystal ball or anything that anyone can do to say you'll need exactly this much data and, with certainty. But to help utilities with longer term planning, we usually advise our customers to plan on field verifying at least 10 to 20% or more of the unknowns, depending on the goals of the program. It's really important to note that there will probably be some services that even after that many field verifications, the model can't strongly classify as either lead or non-lead based on the model's predictions. And those would remain as unknown and could be resolved with additional field verification. But it's also important to note that these percentages, that 10 to 20% estimate or more, those are going to be higher in smaller systems. They may be lower in massively larger systems. So this is just to give an idea. So let's look at some more examples of model results. And I can talk a little bit with each model result, how the utilities had different numbers of field verifications and percentages and things like that. So you can get an idea of what that histogram looks like and how many are left in that middle yellow category with varying levels of field verifications. So this is a medium-sized utility. They're located in the Northeast. They had about 20,000 services, all of which were unknown when they started this initiative. They field verified roughly 5% of their utility side so far, and 13% of their private side unknowns so far. And this is what their histogram looks like after those field investigations. So it's the model's starting to get pretty clear on what it thinks is non-lead versus lead, and the unknowns are getting smaller. And then the next example is a tiny system. Well, I shouldn't say tiny, that's a little subjective, but it's a very small system in my perspective. In the Northeast, they have 2,500 services, all of them unknown, but they only have unknowns on the private side. They verified about 850 of their 2,500 unknowns. So that amounts to about 28%. And this is what their prediction plot looks like. So they still have some more, yellow bars to resolve in the middle there. Those yellow bars equate to us saying the model can't currently classify these as, strongly one material or the other, and they merit further investigation. And then the next example is a large utility in the Midwest. This one is objectively large. They have about 160,000 service connections, about 70,000 unknowns. So far, they have verified about 3% of their utility side unknowns and 2% of their private side unknowns. So they're getting started. I would say they're in like the first quarter of their journey. For about a total of 4,000 service lines that have been field verified to date. And this utility only has galvanized services. They don't have lead. So we're using the model to try and figure out which of their unknowns are potential galvanized so that those can be evaluated as to whether they're GRRs or not. So they're focusing on the yellow and orange bars for now, and they can really deprioritize that large blue bar. And then a couple more case studies. We have a couple of utilities that we've worked with. They iterated through several model runs alongside targeted field verifications. And they did get to a point where they were able to submit the October inventory with 0 unknowns. And this is significant because they were able to field verify a statistically sound subset of their unknowns and rerun the model multiple times. And as a result, they have high confidence that their remaining unknowns are not lead or GRR. And notably, neither of these utilities have any known lead at this point. They have galvanized, and we're using the model to determine if potential galvanized services need to be evaluated by an engineer to determine if they qualify as a GRR or can be called non-lead. So I have thrown a lot of numbers at you, pictures, charts, data. The good news is there's a simple takeaway. If you're trying to understand whether it will be valuable for your water system to use a predictive method, something to consider is the number of unknowns that you have and that you're trying to resolve. And it will also depend on whether or not there's lead or galvanized requiring replacement in the system. So we have some general guidelines here. If a utility does have lead or galvanized requiring replacement, known to exist in the system, machine learning is the best course of action. If we're talking about machine learning versus statistical methods. So in that case, if a utility has less than 3,000 unknowns, machine learning might not be extremely helpful. Depending on your field verification options, you could potentially physically verify all of these properties and not even worry about machine learning. Again, it really depends on what the risk tolerance and the budget and the field verification options. There have been exceptions where it has been helpful for utilities with fewer than 3,000 unknowns, but it's just a general guideline. If you have between 3,000 and 500 unknowns, you're kind of in the middle. Machine learning could be helpful, but you'll really need to scrutinize the cost-benefit analysis. And of course, we can help you with that. If a utility has more than 5,000 unknowns, and they do have lead or GRR in the system, this is where we start to be much more confident in saying that machine learning will be helpful and valuable in helping to reduce those unknowns in a cost-effective way and target your field work towards probable lead or galvanized service lines that need to be replaced. So in this case, it's likely a better option than field verifying all unknowns. And it's important to note, again, that there are always exceptions. These are just general guidelines. So then for utilities without lead or GRR, we don't use machine learning. We use statistical analysis. And in that case, you would need a minimum of 300 to 400 field verifications. Unless you have fewer than 1,500 services, then you can calculate it at 20%. But depending on the unknowns, this number is calculated. But it's a relatively small, reasonable number. And if you want a smaller margin of error, you could increase that sample size for, less uncertainty, right? But generally, we don't have the same concerns about the cost-benefit trade-off when applying the statistical method for utilities that have no lead and no galvanized requiring replacement. And this is especially true here because we're talking about systems that, again, are pretty certain they don't have lead, they don't have GRR, they just don't have the records to back that up. So it would be hard to justify digging up every single service line in a scenario like this, and statistical analysis becomes a really valuable technique. So then we've looked at, again, a lot of histograms, charts, and data, things like that, which are helpful to understand the big picture, but it's important to be able to view the model's predictions on a map as well to identify potential hotspots for lead. So this is our LEDcast dashboard, and the map is showing the results of the predictive model. The red and orange are areas with significant number of properties that have a high probability of lead. And as the video showed, you could zoom in and see the individual property level. So many of the utilities that we work with use this view. For example, if they're in an area for like routine field operations, they can open this map and use the model's predictions to guide some opportunistic field verifications of nearby service connections that may have a higher probability of being lead or galvanized, or even just a middle probability of being lead or galvanized that won't be able to be strongly classified by the model at this stage. All right, so I want to thank you all so much for listening and sticking with us. We gave you a lot of details. Definitely open to any questions that you might have. And if you would like to learn more about who we are and what we do, feel free to use your phone to scan the QR code on the screen. Thank you. So I'll turn it over to Jay for Q&A.
First, thank you so much to the audience for joining us today. And thank you so much, Katie and Wendy, for representing us and being such informative speakers. Let's get into some Q&A questions. Katie, I've got one for you that we'll start off with about predictive modeling results. Are predictive modeling results subject to the validation pool, and are there strategies for success?
You're on mute.
Yep, check your mic, Katie. Yep.
Sorry, thanks. Too safe there. Yes, they are subject to the non-lead validation pool, along with other exploratory methods. So basically, if it hasn't been field verified on both the private and utility side, and if you can't demonstrate that it was installed after the lead ban, then it is subject to the non-lead validation pool. And one strategy to success, there's a couple that I would say is the iterative process and the continuous field testing as you go, because you're going to be less surprised, when you go to perform non-lead validation than if you had just run it once and left it up to goodwill to hopefully pass, which we're not advising. It's an iterative process. And the second success strategy could be, splitting up the validation pool among those exploratory methods, so that, let's say you find a record that said it was non-lead, but it turns out to be lead or GRR. But you didn't find any predictions that, weren't lead or GRR. The whole pool isn't compromised, and the whole swath of properties that you classified with that method isn't, compromised based on one method failing, if you will. I don't know if you have any methods to add there, Wendy, but.
No, I think one of the things, though, that I would like to add, since we brought up the validation pool, is, you don't have to wait until year 7. It needs to be completed by year 7. But this is something that systems can be actively looking at and testing their validation throughout. So that way, when they actually go to do their final validation, they're not, you're not caught off guard, and what you're going to see, and that you've set yourself up for success.
Great, thank you. Here's one that came in through the audience. What if a system has no known lead and doesn't find any through a statistical method, but does find galvanized lines? What information would they need to collect to demonstrate that the galvanized lines are not GRR?
Yeah, so this one is, oh man, it's a good one, and I'm so glad you asked. Because let's say you go out and do your representative sample, and you find 5 galvanized services, and you can prove those 5 are not GRR. Well, we might ask, how does the proof that 5 galvanized are not GRRs apply to all other possible galvanized in the system? So most utilities and regulators are looking for a little more, like in this case, a little more than just like, we didn't find any GRR in the sample, but we may have more galvanized out there, and we don't have strong evidence that none of the galvanized are GRR. So for example, some of the utilities we worked with have looked back at and been able to find like historical like meeting minutes and policies and procedures and go-bys that stipulated, lead was never to be used either in certain areas of the town or like, throughout the system, to kind of provide a really strong narrative that any galvanized you could find is really, really unlikely to be a GRR. So it really just depends on the utility, but yeah. I don't know if you have any thoughts on that, Wendy, but that's a tough one.
Yeah, no, I think you covered that.
Cool.
Thank you, Katie. We've got a couple from the audience just about field inspection. So two people had asked about this, and one specifically, what field inspection method did Middlesex use? And then a little more generally, what methods of field verification do you see most utilities using?
Yeah, that's a great question. Middlesex used so many different methods. They used, I think they used customer self-reports that were verified with a photograph that were verified by an engineer. They used interior inspections through canvassers. They used potholes. In some cases, they had test pits. The potholes have a photo taken and, you know, some evidence of the inspector being able to demonstrate what the material is, like a magnet test or a scratch test or something like that. And then the key to them being able to get so many is for many years, like preceding these regulations, they made it very easy, and they incentivized their field staff to capture the information that they were observing in the field over the course of normal field work.
I will say that down here, especially in southern Texas and along the Gulf Coast, we're very fortunate because our service lines, you know, we don't have to worry about freezing. I mean, it has happened on occasion, and it's historic when it does happen. But in general, our service lines are fairly shallow and close to the ground surface. So while we don't have basements, so you can't go inside a customer's home and view the service line inside the home, you know, it is much less invasive to dig up the service line or inspect the service lines, either, you know, through some sort of test hole, which would not need to be shallow, or the other arrangement that we see a lot down here is that rather than coming up through the bottom of the house, like through the slab, they will actually, the service lines will come up out of the ground and then enter into the back of the house. So that's another really good source or location where you can see the service line material without doing any kind of excavation or entering into a private customer's home.
Great. Thank you both. Thank you, Katie. Thank you, Wendy. I think we've got time for maybe one more. This came through from the audience. Generally, what percentage of service lines need to be field verified to teach the model?
Yeah, that's a great question, and I like it because it's so nuanced and hard to answer, but it's a great question. So you can consider it in 3 phases. We can start with a sample size of 300 to 400 field verifications. That's per side of, like, so you could get both sides, or you could do separate sets of 300 to 400 for private side and utility side. That'll get us started, and then we want to iterate until we have at least 1,500 to 3,000 in the test set. And that's calculated with statistics. It's just having enough in the test set itself, which is only 20% of all of the field verifications you have that's held out of the model to measure its success, to have a 95% confidence level. So first 300 to 400, second 1,500 to 3,000. And then after that, it gets really tough to answer. But our general guideline based on what we've seen is over the long-term plan to do at least 20 to 30%, 10 to 20% or more, to reach, you know, stable and reliable model results, and then to eliminate as many unknowns as you can.
Okay, thank you so much, Katie. I think we're at time, so one last thank you to our audience for joining us today, and a massive note of appreciation to our 2 speakers, Wendy Lundeen from CDM Smith and Katie DeHeer from Trinnex. You can find both of them on LinkedIn. If you'd like to learn more about Trinnex, you can find us at www.trinnex.io, and if you're interested in our predictive modeling solution, go ahead and search for Leadcast Predict online and you'll find us. So thank you again for joining, everybody. Have a good rest of your day.
Thank you.
Thanks.